Welcome to the video tutorial series of Building Architectural Walkthrough using Unity. My name is Stefan Boykens, and I'm an architect engineer working as an academic researcher in Belgium. I've had quite some experience with different modeling and visualization software tools. Unity has been my preferred environment for interactive 3D, as it is flexible, has a good workflow, and provides a free version running on Windows and OS X. Through the course of this video series, we will explain how you can use the Unity game engine to build a real-time walkthrough from an architectural model. This video course is not a complete introduction to Unity, so we assume that you already have a basic understanding of Unity. However, as a series is aimed at architects and students who might not have experience with real-time development, we will show you all the steps that are required along the way. Luckily, Unity is quite accessible, certainly for people with experience from 3D modeling software. While the professional version of Unity is recommended for architectural visualization, you can use the free version of Unity for this course. We use mainly SketchUp, Archicad, and Cinema 4D. You can follow along in the 3D modeling software of your choice. Access to Photoshop or GIMP is recommended as well. The course is split into 8 sections. The first section discusses the import of architectural models in Unity. We illustrate this with 2 different modeling applications. We start with Trimble SketchUp, which is an efficient and fun modeling software, and is used widely by architects and designers. We also illustrate Graphisoft Archicad, which is a building information modeling software for architectural design and construction documentation. The workflow is more elaborate, but is still straightforward when combined with Maxon Cinema 4D. For other software systems, such as Revit, Rhino, AutoCAD, similar workflows can be followed. To ensure optimal performance, we will discuss a few techniques you can apply, such as culling, splitting models, and refining import settings. The following sections will each show you a new series of techniques to be applied for the creation of a walkthrough. In section 2, we learn how you can walk around in your scene and how you can apply animated characters to it. Third section, on shaders and textures, will describe how you can set up materials to make the model look good using different techniques. Fourth section will discuss lighting and shadowing. We will set up a daylight scene and apply both real-time and static pre-rendered lighting and shadows using the integrated Beast Lightmapper. In section 5, we talk about animation. We use the integrated keyframe animation system from Unity. The following 2 sections will introduce you to scripting. While you can do quite a lot with the existing tools and pre-packaged scripts, it is very important to have a basic knowledge of scripting to define your own interactive projects. Luckily, the scripting system in Unity is well integrated. Some basic background experience with scripting will be really beneficial. Finally, we will discuss how we can publish our walkthrough into some of the platforms supported by Unity. In this first video, we got an overview of the different activities we will perform throughout this video course. Our next videos will introduce you to the workflow of using Unity in combination with architectural modeling software. In this video, we will explain how we can transfer a SketchUp model into Unity. At the end of this lesson, we have the model loaded inside the Unity scene viewport. Since Unity cannot directly import SketchUp files, we have to convert the model to a more suitable format. This depends on the version of SketchUp you have available. We created a typical SketchUp model with faces, some groups and components, and materials applied to the geometry. From the File menu, we can directly export a 3D model into different formats. If you have SketchUp Pro, you can export as FBX. It can be used directly with Unity and is the preferred option. Set the units to meters, so the model can be imported at the correct scale. We save the model directly into the Assets folder, preferably in a subfolder such as Models. When you switch back to Unity, the model is automatically imported. It can now be dragged onto the Hierarchy tab or directly into the Scene window. Unity reaches SketchUp object names and hierarchy, provided you have modeled using groups and components. To ensure the model is loaded at the correct scale, insert the Cube Game object. By default, the Cube Game object is 1 by 1 by 1 meter, so we see that the SketchUp model is at a different scale. Correct this by selecting the SketchUp model in the Project tab and set a scale factor to 1 and press Apply. In case you don't have the Pro version of SketchUp, it still is possible to use the free Make version, which supports the Collada format. We will use the default options, but we see that we have no setting for scale or units. When you drag the model into the scene, you will notice that the scaling is not correct. In this case, we will use a scaling factor 0.0254. Now we see that the two models are exactly on the same scale. With any addition of SketchUp, there are two frequent problems. First, ensure that all materials that have been generated by Unity have a correct texture applied, and you can switch the main color of the default material to white. Secondly, all faces that are reversed inside SketchUp will end up being invisible in Unity. Back in SketchUp, switch on the monochrome face style. Faces displayed in blue are reversed. Right-click on them and select Reverse Faces. You will also have to switch the applied material. It is now placed on the backside. In this video lesson, we explain the conversion of a SketchUp project into Unity, using either FBX when using the Pro version, or Collada when using the free version. In the next video, take a look at another software for architects, as this will require a different workflow. In this video, we will explain how we can transfer an Archicad model into Unity. If you are not a user of Archicad, you may skip this video and the next one. However, when using Revit or Vectorworks, the workflow is very similar. Since Unity cannot read Archicad files, and Archicad has no direct support for FBX or Collada, prefer to use other software to make the conversion. We use Cinema 4D and the Exchange add-on for Archicad to add support for exporting a C4D file directly from Archicad. While Archicad is able to export OBJ, 3ds and Google Earth files, they don't lead to the best results when used directly in Unity. It is a solution, however, when going from Archicad to other 3D software, such as 3ds Max or Blender. In Archicad, we created a model of a regular single-family house which we want to prepare for an interactive walkthrough. From the Archicad 3D window, choose a suitable view which only displays the objects we want to have included in the export. From the Design Extras menu, we can set the Cinema 4D export settings first. For the most flexible output, choose the By Class option and leave the geometry scaling factor to 1. Save the file in the Cinema 4D format from within the 3D window. Ensure the model is saved in the Unity Project Assets folder. When you switch to Unity, it will convert the model from the C4D format to an FBX file in the background, provided you have Cinema 4D installed on your computer. So while we did not open Cinema 4D ourselves, Unity did this for us in the background. When you drag the Archicad model in the scene and place a default cube next to it, we see that the default scale, 0.01, is suitable for this particular conversion. There usually are no backface problems with Archicad. Materials are automatically retrieved, and a model hierarchy from the export is respected. We see separate groups for walls, windows, roofs and slabs, and other building elements. Each Archicad object becomes a separate group, which contains the different polygonal meshes. Are we there yet? Not quite. We just exported the Cinema 4D file directly from Archicad into a Unity project. In this video, we explained how we could convert an Archicad model into Cinema 4D using the Exchange add-on, and even load it automatically in Unity. But we need more control, and we'll continue in the next video with the actual link between Cinema 4D and Unity. In this video, we will continue the explanation on how to transfer an Archicad model into Unity. In the previous video, we already converted our Archicad model into Cinema 4D format. However, there were no questions asked and everything was converted in the background. We cannot make changes directly in Unity, but we can edit the Cinema 4D file. Sometimes models don't come in correctly or need more editing. We had occasional mapping errors, where texture ran messed up, scaled wrongly for certain parts of the model. We can also not define animations from within ArchiCAD, so if you want to include them, it should be done inside Cinema 4D. However, this would lead us too far in this video, so we focus on the texture mapping. We might occasionally have incorrect texture mapping applied to some objects, which can be corrected inside Cinema 4D. Double-click on the model inside Unity to open Cinema 4D with this project. Most mapping problems can be solved by applying cubic rather than default UVW mapping. Usually, you would use the length and tiles parameter inside Cinema 4D texture tag to adjust the scaling for this object. But as we experienced, this modification is not retained in the conversion to Unity, so we need to use another method. Switch to the texture editing mode and activate the Enable Axis option. Now we can scale the gizmo, the cubic gizmo, to the 33 centimeters in all directions. This modification does not adjust the length and tiles parameter and will be retained when going back to Unity. Save the Cinema 4D model and switch back to Unity. After a short while, the model in Unity is updated with the new texture coordinates. In the last two videos, we explained how we could convert an ArchiCAD model into Unity by using Cinema 4D and the Exchange add-on as an intermediate conversion tool. The same workflow can be established with Vectorworks and Cinema 4D, or, if you prefer, Autodesk software, where you can combine AutoCAD or Revit with 3ds Max. In the next video, we will review the model update process, as this is an essential aspect of our visualization workflow with Unity. Now we know how to transfer models from two different applications. It is important to understand how changes in the model can be integrated back into the Unity project. While you might assume that all your work is lost if you need to update the model and re-import it, Unity provides a flexible workflow. All assets can be refreshed and updated in the project at all times. Since each model in the Assets folder stores its importer settings, we can create a new version of the geometry to be loaded again, still retain our adjustments inside Unity. When you export the updated version of your model, you have to overwrite a previous version of the file using the same name and same export settings. Depending on the software you use, you might have to note down these settings when they are not retained. Let's see how this applies to a SketchUp model. Make a small change and go back to the export dialog. In the options of the export in SketchUp, you need to ensure that we use the same model units and other settings as last time. Be sure to overwrite, place the model already exported in the Assets folder of Unity using the same file name. The moment you switch back to Unity, it detects that the model source has changed and updates the instance in the project. Depending on the size of the model, this might take seconds or even minutes. In the case of ArchiCAD and Cinema 4D, it is also possible to add geometry or even record animation in Cinema 4D, which is important alongside the geometry. However, when the ArchiCAD model changes and is merged into the Cinema 4D file to update its geometry, we lose specific changes to the ArchiCAD geometry that occurred inside Cinema 4D. We only retain objects outside of the hierarchy, but also material adjustments, render settings, and other animations. Let's illustrate this with a small change in the ArchiCAD model. Copy one of the windows to the side of the building and save back again the 3D model. Since this is a change, we will save it outside of the regular Assets folder, second version of our model. Then we go back to open Cinema 4D. Then now we can open our last model. This is a model that is linked in Unity, but it is not updated with the previous changes. You might have made some modifications here. Instead of simply opening a model, we will merge the updated version of the geometry and load it into the current Cinema 4D project. If we look back to the side, we see that the additional window is there. Now we can save this model and go back to Unity. I see that this version of the model will be reflected in Unity. With the new windows, the model itself is at exactly the same position. Change in the scene is simply the update of the geometry. To conclude, Unity is a system with a very well thought out workflow. This was illustrated in this video by showing how models can be reloaded when they are modified. Applied transformations, materials and import settings are retained in Unity, even after changes to the model file. In the next video, we will go over some options we have to improve the performance of the project. In this video, Improving Performance, we will explain how we can improve our model by optimizing its settings and by reorganizing our scene a bit. Architectural models tend to be quite large and can slow down real-time projects, certainly on mobile clients. While Unity provides several optimizations behind the scenes, we can improve performance ourselves as well. We will look at prefabs and culling. First, toggle the Stats button in the Game window to display an approximate frame count and a summary of the used geometry. If you export the whole project as a single model, it becomes very static. In interactive scenes, we want to have more control and need to adjust individual objects separately. Even though our models contain a usable hierarchy, it is more efficient to split them up. The next step, we create a separate model for objects that are to be repeated in the scene, such as a chair. We load the furniture object from SketchUp as a single file and export it as an FBX file into the Unity Assets folder. The chair model automatically loads in Unity, and now we can drag it into an empty scene. We can easily place copies by pressing Ctrl or Command D with the object selected. Since loaded models are treated as prefabs, they all stay connected to the source object. Although this does not actually speed up rendering, it helps in project management and is highly recommended. Unity performs so-called culling on different levels. Culling is when the Unity graphics system skips objects, geometry, that is not visible. We already saw culling in action when Unity hides the backside faces of geometry. With dynamic culling, Unity also hides objects which fall outside our camera view. This is noticeable in the Stats window. Activate Play mode and move the camera left or right, so we can see the amount of chairs that can be seen. When you set a static attribute for objects, you indicate that they will not move and can be optimized by the graphics system. This is called static culling. However, it is only supported in the Pro version of Unity. In the free version, this has no direct performance impact. However, we will return to this toggle later on, so that this is a good habit to indicate which objects are standing still in our project. To facilitate culling, it helps to split very large objects or scenes in smaller chunks, so they can be toggled on and off when they disappear from the camera view frustum. If only the tiniest part of an object is visible for the camera, it cannot be culled. The more geometry we load, the more effort it takes. So remove every detail from the model that is not contributing to the real-time project. This is especially important for architectural models that tend to include excessive geometry for every part of the building. While we are not able at this point to get into more detail about other possible performance improvements, we have shown at least the basic techniques to manage a project for better performance. Use prefabs and try to limit the amount of geometry at all costs. This ends our first section on importing architectural models in Unity. Our next section will focus on walking around in our project. Welcome to section 2, Navigating an Architectural Model. In this section, we'll add navigation into our model. This will allow the user to walk around freely and explore the design. We will discuss two different control setups and also show you an example of loading a different character. Finally, we'll add an additional view from the top as a minimum. In the first video of this section, adding a first-person character, we'll explain how to add a first-person character to walk around. Since a first-person character is fairly complex to set up and involves scripting, Unity provides a ready-to-use navigation system. This requires the import of a package of assets that Unity provides from the Asset Store, an online integrated store for Unity assets. We'll use the sample assets package from Unity, which contains a prefab you can drag directly into your scene and configure with parameters. Prefabs are game objects that are stored as asset files and which can be reused in all scenes of your project. When you change a prefab, all copies will automatically update. We already showed you how to load a model from SketchUp and Archicad. Now open the Asset Store tab, menu, and look for sample assets. At the time of recording the video, they were still in beta, but are meant to replace the default standard assets that might still be installed with Unity at the moment you watch this course. After you have created a free account in the Asset Store, you can download this 200 megabyte package for free. When the download finishes, Unity will show the contents of this package file, which is an archive with assets, scripts, models, and even an animated and textured 3D character. For convenience and to ensure that nothing is missing, select All and press Import to load the whole package. After quite a few moments, the assets are loaded into the project. Navigate inside the Project tab and fold out the Sample Assets, Characters, First-Person Character folder. Select the First-Person Character prefab in the Prefab folder and drag it onto the Scene view to place an instance in the scene. Also, add a plain game object, which acts as our ground plane. Reposition it, set big enough scale to make sure that we encompass quite some place. This will be our ground. Select the first-person character and move it upward. This will be the beginning position of our character. Beware that if you come from a CAD or BIM background, that Unity uses the green Y-axis as the vertical axis instead of the Z-axis, which is displayed in blue. Navigating a first-person character requires the use of the mouse to aim in a particular direction and the arrow keys or the WASD to move. However, if you don't use a QWERTY keyboard like I do, this is not a very comfortable setup. Luckily, Unity also supports an attached gamepad or joystick, which usually can be used directly. You might see some warnings in the console that there are two audio listeners. This is because the default camera and an additional camera that has been included in the first-person character are both listening to the sounds that are played. Also, the main camera is hiding the display of the first-person camera, so we remove the main camera. If you press play now, warnings should be gone. The first-person character now you can walk around, use the mouse to display a certain direction, and use the arrow keys or the WASD keys to move back. We can further explore some of the properties for the first-person character control if you select it in the Hierarchy tab and look at the Inspect. First-person character component script defines the speed of walking and running and the jump power, how strong you can jump. A simple mouse rotator is responsible for the reaction on moving the mouse around. First-person head bob script adds stepping sounds and a bouncy up and down movement while walking. You can disable this component if these movements disturb you or your. This object uses the physics engine, so it also needs a rigid body and capsule collider component. The mesh renderer itself is turned off, so you cannot see the capsule that represents yourself. You might have noticed that we can safely walk around on the ground plane but we can still pass through the walls of our house. This is something that we'll solve in the next video. So, within this video, we learned how to walk around our project, use the predefined first-person character, provided as part of an asset store package from Unity. That was not too hard, was it? To video 2.2, preventing running through walls. In the previous video, we noticed that we could walk right through walls. We are also not able to step onto the stairs of our model. In this video, we will look at colliders. This is geometry that is used to check if objects overlap, pass through each other. This video will add colliders to our project and also briefly discuss other possible colliders. In game engines, geometry is not automatically set up to collide, prevent extensive collision calculations. By only adding colliders where needed, we can limit these calculations. Let's check where we have arrived after our last video. In the Project tab, look at our model. Select our model and look at the inspector to adjust the importer settings. We have to activate Generate Colliders and press Apply. This generates a mesh collider for all the meshes in the model. You can see that every object that has a mesh now also has a mesh collider component. We can check that it works by pressing play now and walk through our building. Now we will automatically stop when we bump against the wall. So, in most cases, we want our architectural models to have colliders for every mesh, and this is easily set by the importer. However, there are cases where this is overkill. If you have very detailed geometry, such as plants or chairs or even doorknobs, they might slow down Unity considerably. In some cases, our controller might even get stuck. It is possible to be more selective and disable certain colliders. If you have a model with closed doors, or you have a wall where you want to pass through, we can disable their collider, which would allow us to walk through them again. While this is not very realistic, it solves at least a problem in initial projects when you are not able to enter a door. So what about regular Unity geometric objects, such as cube, cylinder or sphere? They all have a default collider applied. Add a few cubes, maybe a sphere, if you press play now, you can see that the sphere will prevent us from walking through. Same with the cube. If you look at the properties of these objects, you see that the sphere has a sphere collider and the cube has a box collider. Each game object can only have one collider component of each type applied, but you can combine a box collider and a sphere collider for more control over their collisions. Collision detection takes quite some resources and slows down the scene. You can replace complex colliders in many cases with a basic box or capsule collider. You can remove the mesh collider or disable it in the FBX importer settings for a model. Convex colliders, such as box, cylinder or sphere, are easy to calculate. Concave ones, such as the mesh collider, are more demanding and should be disabled or replaced where possible. You can create a compound collider by combining different collider types in one object or adding multiple objects together, each with their own collider. Since collider geometry is invisible, it poses no visual problems, yet still ensures that we steer where the user can walk. Many games apply invisible walls to prevent users from stepping outside an allowed area. This is easily done in Unity by adding a cube game object and disabling the mesh renderer component. The attached box collider will still prevent objects from passing through. This concludes our second video on navigating, where we added colliders to our project and also discussed how and when to use them. Remember, you can disable or even replace colliders to fine-tune the game performance. The next video will discuss an alternative character setup. In the third video on navigation, we will talk about the third-person character, which is an alternative character setup where the player watches a 3D animated character, usually from behind and slightly above. In this video, we'll add a third-person character and properly set it up. In architectural visualization, it is often easier for users to navigate a third-person character using arrow keys. People who are not accustomed to 3D games might have trouble with navigating a first-person character around, although that allows for more control over the direction in which you look. Since it is even more complex to prepare a fully animated 3D character, we'll use pre-created characters. Luckily for us, the sample assets package from Unity we loaded in a previous video also includes a usable setup. First, remove the first-person character from our scene and drag the third-person character from the sample assets prefabs into our scene. If we would press play right now, we would get several setup problems. And we find no main camera. Luckily, this is straightforward to solve. Within the sample assets, there are a few different camera prefabs. We will drag the multi-purpose camera rig into the scene. In addition, we'll also add a basic directional light to remove the dark lighting we get in the project. When we press play now, this specialized camera rig by default will automatically follow our main character around, wherever he goes, using the AutoCam script component. There is also a protect camera from wall clip script component, which prevents this camera to fly through walls. This is very handy, especially when we walk inside a building. Try to walk around a bit. Press Shift to have the character walk instead of run. Space to make him jump. With this setup, we cannot really steer where we are looking at. If you want to allow the user to use the mouse to look in all possible directions, remove the multi-purpose camera rig from the scene and try the free look camera rig instead. Now you can pivot around the character with the mouse and still walk freely with the same cursor keys as before. Both setups provide a complete animated character, set up to be steered by the cursor or alternatively by a gamepad. The difference here is mainly in the camera follow behavior. The third-person character component defines the movements, where the third-person user control allows you to define how he moves relative to the camera. You can also set if the character walks or runs by default. So there we are, a fully animated 3D character which we can steer around our project easily. Of course, the internal behavior and scripts are provided from the sample assets package. In this video, we replaced the first-person character with the third-person character. It took a small effort to refine the camera setup, but in the end, we have a chance to experiment with the two most common navigation schemes. The actual scripts that do the hard work are a bit too complex at this point. The main setup is easy to reuse. Our next video will take a look at switching to a more regular character, better adapted to architectural visualization. Welcome to video 2.4, loading a different 3D character. While the model from the previous video is usable, it is probably not the best style of character to use in an architectural visualization. In this video, we show you how you can download an alternative character with animations from the asset store. While it is possible to model, texture, rig and animate a 3D character, this takes an enormous amount of time. In architectural visualization, it is common to use prepared assets and focus on the design of the building rather than the details of the model. Open the asset store, and when looking for a usable character, we landed on content from Mixamo, which specializes in 3D characters and associated motions. They have a few basic characters available without cost, but the animations have to be bought separately. We decide for the popular Mixamo assets as their characters and animations are all compatible. When looking at other characters and animations, they might not directly work with each other or require additional customization using the integrated Mechanim animation system. After looking around, we settled for man's everyday motions, which is a male character with 10 different basic motions. It costs almost €30, which still is a fair price. When you buy the packet, you can import it directly into Unity, just like any other package. This package includes an example scene, which illustrates a character with animations and a controller scheme. This setup uses a particular method of animation control called root motion, where the movement of the character is directly derived from the actual motions. This has this distinct advantage that the motion is more natural and the feet don't slip. Let's go back to our regular scene and remove the third-person character from last video. Drag the Justin prefab into the scene and position him in a suitable place. You can see that several animations have already been applied, and there is a root motion computer and a root motion character control script, which defines the keyboard actions alongside a regular character controller component. If you press play now, the character starts moving. This setup uses WAD to move forward or rotate, and you can hold Shift to have the character run. Arrows are not recognized in this example script, alas, and also the backward movement is missing. There are a few warnings about finding certain components, but the script does find them automatically at run. Beware that the camera is not following the character automatically, like we had in the previous video. Here we illustrate a quick and rough method without resorting to scripting at all. Add a new camera, increase the depth so we are sure that this is the camera we see above the others, and drag it just on top of Justin to make it a child of the character. A child follows the movements of its parents automatically. Now we can position the camera relative to his parent. Set the X to 0, Y to 2, and the Z to -2. When Justin walks, this camera stays fixed about 2 meters behind him and slightly above his head. While this is a very crude setup, it is a quick fix without requiring any scripts at all. You see the same warning about audio listeners. However, when you use scripting, you can make it smoother by using interpolation to give it a slight delayed movement, just like we had third-person character example setup. Let's remove this camera and reuse the free look camera rig. In this case, we get an error. Variable target of FreeLoCam has not been assigned. If you look at the FreeLoCam, the target variable is where the camera would look at. So, select FreeLoCam and drag Justin as a target for the FreeLook camera. If we press play now, the last errors are gone. The camera is able to follow Justin around the same way as we had with the previous video. We can also apply the multi-purpose camera rig instead of the FreeLook camera rig, as long as you ensure that Justin is set as a target for the AutoCam script. And now the camera follows Justin around when walking. In this video, we replaced the default third-person character with a more suitable one that was bought from the asset store. This did provide a different setup, so we had to do some additional work to get the camera correctly follow the character. But this is a very usable result and with a more suitable character. Our next video will use a similar trick to add a top camera and a small corner viewport above our main view. Welcome to video 2.5, adding a minimap. In game navigation, you are often helped by a radar view or a minimap. This displays a scene as seen from above and is placed above the main screen. In this video, we'll use a second camera and configure it without scripting to add a second display above our main camera. While not the most elaborate setup, this is easy to do and is directly usable. You can start from the scene from one of the previous videos. The process is the same in each case. First, create a new camera. This adds a new camera in the project, which is displayed above our main camera. Remove or disable its audio listener. At this point, the game window you see in the camera preview shows a part of the scene and the blue background color. If you set the clear flags to depth only, the background becomes transparent. This camera blocks the view of the other camera, so we have to adjust its viewport rectangle in the camera component properties. We chose x equals to 0.74, y to 0.01, and the width and height both set to 0.25. This places the camera in the bottom right corner, but you can adjust this to your liking. Now adjust its projection by switching it to an orthographic projection, as this makes more sense for a camera top view. The next step is changing the orientation so the camera looks down from the top of the project. Set rotation X to 90 degrees. We can also move it upwards by setting the Y position 2 meters. Now it depends on what you want to do. If you simply need an overview, adjust the size parameter of the camera to make it large enough to see the whole scene from above. In this case, the camera stays fixed in its place. We can then attach a large sphere to our character as a child and place it above the roof of our project. Ensure that our minimap camera is placed high enough so it can see the sphere. Now this sphere will be shown as an indicator of our character. A more advanced trick is using layers. This can be used to toggle the visibility of objects for different cameras. Go to the layer dialog. We add 2 new layers. Let's call them minimap and non-minimap. Now we can set the layer for the sphere to the minimap layer, the ground plane, which is part of our model geometry, is set to the non-minimap layer. Right now this doesn't seem to have any influence, but the moment we adjust our camera, we can set them to ignore particular layers. Our minimap camera will ignore the not minimap layer. Our current main camera, in this case hidden inside the multipurpose camera rig, can be set to ignore the minimap layer, so the sphere is not visible for the character. Now the plane is hidden from the minimap and the sphere is hidden from the main view. If you want to follow the character with the camera, you could attach the camera as a child to him, so it heads all movements and rotations. However, for more complex setups, we will need some scripts. In this video, we illustrated a very simple setup, but for more elaborate setups, such as displaying lines or icons or inheriting particular movements but not rotations, you definitely need to write a script. This is the last video of the section on navigation. The next section, we will apply shaders and textures to our setup. Welcome to section 3 of the video course on architectural walkthroughs using Unity. The first video of this section discusses textured materials with bump and specular mapping. Here we learn how to improve our initial, rather dull textures as imported from the CAD or BIM system. While many CAD and BIM systems support textures to visualize materials, they usually apply simple, plain texture maps. They are good during modeling, but are rather dull in a real-time environment. By using higher resolution textures, with complementary maps for additional material characteristics, we can highly increase the visual quality of the model. We will focus on adding some bumps to our materials first. There are many possible sources for better texture maps that are usable in an architectural context. We will illustrate the process using the Arrowway website. They specialize in real-world building textures for 3D rendering. They provide a low-resolution version of every texture under a Creative Commons license, which provides sufficient detail for real-time applications. We browse to the Edition 1 catalog and retrieve the Bricks 002 texture. We can see a preview on the page and also real-world measurements, which help us to scale the texture adequately. download the RAR archive and unpack it. Switch back to Unity and drag or import the 3 maps into a materials folder. Create a new material. You can do this by right-clicking in the Assets tab or from the Assets menu. Call it AW Bricks 002. By default, it uses the diffuse shader. To apply the main diffuse map, use the Bricks 002 D100 texture, as hinted by the name of the texture. Simply drag the texture onto the texture slot of the material. You can also open a browse window up by pressing the Select button. Keep the main color to white. To add bumps, we change the diffuse shader to bumped diffuse. This requires a separate normal map, which will be derived from the bump texture. Drag the Bricks 002 B030 texture into this slot. Unity warns us that this map is not marked as a normal map. You can press the Fix Now button to do so, or follow the manual method of selecting the texture asset and switching the texture type to normal map in the inspector. Derive the normal map from the grayscale image. We can adjust the settings of the map to define how extensive the bumps become. Try a low setting such as 0.05. We usually choose smooth filtering and leave the rest as default, and press Apply. Finally, to also use the specular map requires a diffuse map with a separate alpha channel. We can derive an alpha channel from the grayscale values of the diffuse image, but this is only a cheap workaround. For best results, use your image editing software to turn Bricks 002 S100 G100 into a real alpha channel. Open the diffuse image in Photoshop. Add an alpha channel and paste the grayscale specular image into this channel. Save the image with alpha channel into the PSD format, as Unity can use this directly. The best workflow when using models from CAD or BIM is actually to do this in 2 steps. First, set up the main diffuse map in your CAD or BIM software of choice and define the real-world size. This ensures it is applied correctly in the model. We illustrate this in the Material Settings dialog in Archicad, but it is very similar in SketchUp and other programs. When you now convert a model into Unity, the maps are scaled correctly upon import and can then be improved as explained earlier on. In this video lesson, we explained how we can replace a single texture with a more advanced texture set, downloaded from a dedicated site for architectural visualization. Our next video will add a sky with clouds to our scene. Welcome to the second video of section 3, where we discuss cube maps and how they are used to simulate a sky with clouds. The main background in the default scene is defined by the camera and is a plain blue color. This is not only dull, but also provides little depth or orientation. A sky can be simulated using a seamless texture that is placed on the inside of a giant cube that sits around our scene. In Unity, we can use a skybox. We first start with importing the skyboxes package from the Assets Import Package menu. These skyboxes will be installed in the Standard Assets Skyboxes folder. There are several skyboxes available in the Asset Store and also in the sample assets we loaded in the previous section. Go to the Edit Render Settings menu and drag Sunny to Skybox onto the Skybox material. The scene view immediately displays a full sky sitting around our scene. Render settings are stored inside each scene. Orbit around the scene to see the effect of the skybox in the 3D view. As it sits outside of the model, the view changes correctly when looking around, and while it is only a series of 6 images, it provides a very convincing environment. You can also press play to experience this environment in the game mode. You can define a skybox alternatively as a component for a camera. Select the main camera and add a skybox component from the Component Rendering Skybox menu. Now you can drag another skybox to the custom skybox parameter. To see the effect of this custom skybox, you need to play the game, as the editor will only display the skybox from the main render settings. This method can be useful when you switch between cameras in a scene as a means to toggle between different moods or environments. If we look at one of the skyboxes into detail, we can see that they are composed of 6 images that connect seamlessly at their edges, one for each view direction: up, down, left, right, and front, back. While too elaborate for this course, it is good to know that you could use any 3D rendering software to render these 6 images. Imagine how any series of images can provide your scene with a context that takes no geometry and is very quick to display. This system, however, cannot be used for animated clouds. In this video lesson, we explain the use of skyboxes as a way to add a sky with clouds around our scene. This provides a nice context for our project and improves the feeling that we are visiting an actual site. Our next video will discuss improving our glass in the scene, and we will return to our skybox images for a nice effect. In the third video, in the section on materials, we will create more convincing glass with a custom shader. Since we cannot dive into shader writing, we'll use an existing shader that does the work for us. When you imported a SketchUp or Archicad model, the glass panes receive the pale, transparent, bluish material. However, this hardly looks like glass. Although actual reflections are very heavy to calculate and require a pro license, environment reflections provide a good alternative in a real-time model, and they take little resources. First, create a new shader. From the Assets, Create Shader menu in the Materials folder and call it Reflective Glass. By default, this will be a very simple material using only a single texture. Open the shader with Mono Develop. The shader code you see here was added by Unity from a template, but will replace all code with a complete shader we can download from the Unity wiki. Go to the website wiki.unity33.com, index.php, glass_shader. Go to the glass shader page on the wiki. There are 2 examples for glass shaders, but we only want the second one as this provides the best reflection effect. Simply copy the code of the shader over our default code, but leave the first line so we adapt the name we chose for our shader in Unity. We will briefly go to the shader code to get a rough understanding of what it is actually doing. If you are not into coding, you might find good alternative shaders from the asset store, which can be used as is. The first code section defines the available properties that can be set by the user. Notice that there is a cube map defined, which is used to generate fake reflections. The second section sets a few tags where Unity is warned that this shader is transparent. This is necessary so the screen drawing can reorder objects properly. First, all opaque objects are rendered and transparent materials are blended in. Luckily, we don't have to do anything to organize this. The CG program section is the actual algorithm that defines for each visible pixel on screen that refers to this shader what the color will be. For now, it suffices to know that this shader samples a color from a cube map and modulates or mixes this with the reflection color and output opacity from the alpha channel. Finally, the fallback section says what's a shader to use when the graphics adapter has no support for these particular instructions. Save the shader and switch back to Unity. The shader will be compiled in the background into GPU instructions. Before you can see the effect of the shader, it needs to be used by a material. Choose a glass material that was created when importing your CAD or BIM model and change its shader to Custom reflective glass, the shader we created a few moments ago. The actual reflection effect comes from a reflection cube map. We want to use the same textures as our skybox, so create a new cube map in the Project tab and call it Sunny 2. Now we can reuse the 6 textures from the Sunny 2 skybox into the 6 texture slots of the Sunny 2 cube map. They are located in the Standard Assets, Skyboxes, Textures, Sunny 2 folder. You can drag them to the suitable slots. Also, set the face size to 128 for these textures to have some more detail. Finally, go back to the glass material and add the Sunny 2 cube map into the reflection slot. You can tweak the glass effect a bit with a brighter specular color and a darker reflection color. Final result is best experienced by orbiting around or by walking around in the scene. If you don't like to tinker with actual code, you might take a look in the asset store to find ready-to-use glass shaders. In this video lesson, we explained the use of a custom shader for an improved glass material with a reflection effect. It reuses our skybox textures from the previous video. Our next video will introduce you to the procedural shader type, using substances. Welcome to the 4th video in section 3 on materials and shaders. In this video lesson, we will use an alternative material system, which is providing a more parametric behavior. This can be used for very convincing materials with an easy control over the final look. Regular textures can be quite heavy in games and take up both disk space and memory on the GPU. Moreover, you'll need lots of them when they need to look different. Procedural materials combine embedded normal and specular maps and are defined by a series of parameters. The company Algorithmic has developed a substances system, which is supported inside Unity. There are a few free substances packages available in the asset store, and with their software you can even create your own. Go to the asset store and search for the package 18 free substances. Download and import the package into Unity. The material thumbnails you see are actual substance archive containers. While we cannot modify their inner workings without the substance software, we can adjust their parameters. Select Bricks 032 and take a look at its parameters in the inspector. We can modify parameters such as the amount, bricks in the X direction, depth, and others. To assign a substance to geometry, unfold the archive in the Project tab and drag the thumbnail icon into your object. Don't simply drag the texture, or Unity creates a new basic material from it. These textures are automatically generated from the substance material. Inspect the result in the viewport or the game. Notice you can still tweak the parameters and the material will update directly. To create a new variant from the same archive, use the plus button in the inspector. Now you can define a new look for this particular variant. For instance, choose a different basic color and assign a different seed number for another pattern. Try a few other substances and assign them to objects in your scene. We chose the Pavement 01 substance and assigned it to the ground plane. It even has an age and water level parameter for a more weathered, wet pavement look. Adjust the tiling to get a suitable scale. Some final thoughts. Substances can be very effective. They have small file sizes, yet they generate very complex and detailed textures. But they do increase the loading time of a scene, as the texture maps have to be regenerated at runtime. While you can replace the base RGB, Gloss A, and normal map with regular textures, this loses the procedural qualities and poses no real advantages over regular textures. When you need to apply your own textures, you can take a look at the bitmap to material package, also from Algorithmic. This allows you to generate a substance shader from your own texture map. In this video lesson, we learned about substances, a system for procedural textures that is integrated with Unity. This gives quite spectacular results that are still easy to control. Final projects usually combine textures and substances, so try to make best use of both of them. Our next video will finish the materials section by discussing partly transparent materials. Welcome to the 5th video of the 3rd section on materials. In this final video, we will talk about the use of textures to cut out parts of a surface, to make a fence or an object with holes. When we need to create a model with holes, it takes quite a lot of geometry to model this. This will slow down the game and is not necessary in cases where a material can be used instead. By using partially transparent texture maps, we can define the opacity of a surface with only a small performance impact. We will start this section inside Photoshop to create a texture map with a few holes. Our example is a series of diagonal lines with a bevel effect to give slightly rounded edges. Ensure that you add an alpha channel 2 to contain the transparent pixels. Select the pixels by Ctrl or Command clicking on the layer thumbnail. Press copy and add a new channel in the Channels Manager and paste the channels into it. White will be opaque, black is transparent. Save this image in the Unity Project Assets folder in the PSD format. Create 2 different materials so we can compare the different shaders. For the first material, use the transparent diffuse shader and apply our picture. To correctly interpret our alpha channel to define the opaque and transparent pixels, use the alpha is transparency option. Now we have an actual transparent texture. With this technique, the edges of our fence are rather blurry and not well defined. This might be good for leaves of trees and bushes. Let's define a second material and choose Transparent, Cutout, Diffuse, using the same texture map. This gives much sharper edges, and you can control the edge with the alpha cutoff. This will be a better choice for our fence material. When you need to see the fence also from the back side of the object, you can use the Transparent, Cutout, Soft Edge Unlit shader, which ensures that the fence is also seen from the inside or the back side of the geometry. For fully convincing alpha channels, there are a few additional tricks, and one of them is included in the Unity manual. The manual describes a procedure to dilate the image background, so the edges of transparent objects get a color derived from the material, which avoid bright white edge pixels, which is also referred to as ghosting. In this video lesson, we explain the use of an alpha channel in an image to control opacity in materials. We showed a regular transparent shader and 2 cutout shaders. This concludes 3rd section on materials and shaders. This is the first video of section 4 on lighting. In this video we will discuss the basic light types as provided by Unity. We will try to create a convincing, realistic lighting for our basic scene. Without any type of lights, the scene we create will be dark and dull. Lights are required for ambience and a feeling of what time and season it is in our site. In Unity you can toggle the lighting in the scene window. Without any effect of light, you can clearly see geometry and materials, but everything is flat. However, when we activate the lights toggle, at the moment our scene is dark and very dull, as there are no light sources added. We now add a point light from the Game Object menu. This immediately gives a bright zone where light is emitted. Point lights are the least demanding in real-time projects. They shine equally in all directions, so you only need to concern yourself about their position. We can control range, color, and intensity. Avoid making lights too bright, as this will create pure white areas with no details. It is best to place a few different point lights and vary their color a bit, so objects get a sense of depth. Now add a spotlight to the scene and play with its direction. Here, position and rotation play an important role. The spotlight is projected in a cone shape. Adjust the spot angle either in the inspector or by dragging the yellow handles in the scene view. The third type is a directional light. Its position is not important, as this light will not attenuate over distance, and all light is emitted in a single direction. However, to better see the effect of the directional light, we will disable the other light sources. There is also an area light, but it does not work in real time and requires a Pro license. It is used for light mapping, which will be discussed later on. It is best to apply the directional light as your first main light source, usually being the sun. This defines the exterior light. Also set its render mode to important, so it takes priority over other light sources. You can then apply other light sources to even out lighting and brighten up interiors and all areas that are too dark and flat. Since real-time lighting takes quite a toll on performance, focus on the main light sources first. In this video lesson, we introduced lighting in Unity. They are easily placed, but it is very difficult to get a convincing and varied lighting scheme, especially in architectural interiors. Exteriors are a bit easier, so in the next video, we will focus first on creating a sun. In video 2 of section 4 on lighting, we create a daylight system, defined by a sun and some kind of environment lighting. Most architectural projects can be seen both from the outside and from the interior. The outside is the easiest to manage, as this is largely a result of the direct light of the sun. Remove all our lights and add a single directional light. Name it Sun and position it in the middle of the scene and just above the building. While its position is irrelevant, it helps us in better seeing the objects in the project. Set its color to a yellow that is almost white to give it a warm hue. Directional lights can cast shadows, and this is really required for most architectural scenes. Activate the hard shadow and slightly lessen the shadow strength to 0.8. The resolution can be used to refine the shadow edge, while the render mode indicates which lights get priority over others. This is the only light source that can cast shadows when you use Unity free, and you are restricted to only apply hard shadows. In the transform component of the directional light, you can adjust the X rotation, which is the height of the sun, and the Y rotation, which is the direction of the sunlight. To mimic the effects of the sky that gives our scene some overall bluish lights, we can add 2 additional directional lights. Adjust their rotation with the rotate tool so they shine from opposite directions as the sun. You best do this from a top view position. Move them a bit to the side to assist the aiming. Turn off their shadow and make them less bright than the sunlight. You should also give them a bluish tint, which will colorize the shaded areas from our main sunlight. In this video lesson, we added the sun and created some shadows. At this point, our overall exterior lighting is set up. While it is not yet really convincing, we will revise the lighting scheme later on. In the next video, we will focus on interior lighting. In the third video of section 4, we continue our lighting setup for the interior parts of the building project. Since our directional light casts shadows, the majority of our interior is not being lit by the sun. We compensated this a bit using additional directional fill lights in the previous video, but we can do better than that. Let's first move our viewpoint somewhere inside the project to see how dark and dull our interior model is at the moment. Navigate to a top view in an isometric projection and switch to the wireframe display mode. Add some point lights and place them slightly underneath the ceiling of our room. Add about 6 of them. Adjust their range and intensity and give them a yellow, slightly greenish color. In addition, we can add a slightly yellow spotlight that mimics the sunlight falling through a window. To see what we are doing, we temporarily disable the sun and the additional point lights. For more complete lighting, you can also add one or more bluish lights from the window side, opposite from the sun. While Unity also has an area light, it only works in Unity Pro and not in real time, so we ignore it here. Turn on all lights to see their complementary effect. And finally, to compensate the quite dark and dull ceilings, we can create an additional subtle bluish directional light that can be used to compensate the sun. Make it a child of the sun, positioned in exactly the same place, but with local rotation of 0, 180 and 0 around the X, Y and Z axis respectively. You could call it a fill sun or an anti-sun. Beware that the interior lights could interfere with exterior lights, especially since they don't cast shadows and will shine right through all objects. With some custom scripts or using a culling mask, you could toggle them only when the player is about to enter the room. In this video lesson, we added a series of light objects into a single room to light it up properly. In the next video, we will look at the light mapping process, which could help to create more extensive lighting scheme. In video 4 of section 4 on lighting, we introduce the light mapping process. We will use this to calculate our lighting instead of relying on real-time lights. There is only a single directional light that will cast a shadow, unless you switch to a more advanced lighting system, but then you cannot use the free version of Unity anymore. Moreover, lighting is hard to calculate, especially on mobile devices. Light mapping is a technique where all lighting is calculated in advance and captured in an additional layer of textures that are mixed with the regular materials. Luckily for us, Unity includes a complete light mapping system that is fully integrated and fairly easy to use. However, before we can do this, we need to prepare a few things. All pre-calculated lights will need to cast a shadow. And while this is not possible in the viewport, the light mapping process takes them into account. Hard and soft shadows both work. Then we need to inform Unity about which objects are meant to be fixed by activating their static attribute. Do this for all models, objects, and lights. You'll get a dialog asking to do this for child objects as well, which is what we want. To be able to store the light map on objects, they need a special UV2 mapping type, where each part of the map is only used by a single triangle or face of the geometry. All default Unity primitives have the UVW coordinates already defined. But when loading models from external files, the importer settings can automatically add these coordinates for you when you activate the option Generate Lightmap UVs, which is really helpful. Although most 3D visualization systems do support this process as well. Now we can open the light mapping panel from the window menu and dock it somewhere conveniently. Finally, store our scene, as the light mapping process needs to generate new textures in a subfolder using the same name as our scene. In this video lesson, we prepared our scene for light mapping using static objects, UV2 coordinates, and lights that cast shadows. In the next video, the actual light map calculation is performed. This is the fifth and last video in section 4 on light. Here we will complete the light mapping from the previous video. While we could start the light mapping directly, it is best to first go through the most important settings. We usually start with a fast and approximate first attempt to check the lighting level, and then refine the details a bit at the cost of longer rendering times. After our preparation work, static attributes, UV2 coordinates, and lights with shadows, you can now open the light mapping tab. We leave the default model to single and the quality to high. If you do have a Pro license or are in your trial period for the Pro version, you can set bounces to 2 or 3, which activates an advanced lighting system integrated into light mapping. This is highly recommended, as it takes indirect and environment light into account, which is nice for exterior scenes and essential for interior scenes. It does take longer to render, alas. Ambient occlusion is a rendering trick that accentuates corners and objects that are being obscured by nearby objects. While not completely physically accurate, it creates a convincing depth into the shading of the scene. It is available in all Unity versions and is also highly recommended. To avoid artifacts to occur, ensure your model is a clean, solid closed volume with no hidden faces. The resolution defines how fine you will sample the lighting. Start from a very rough value of about 10 to 15 pixels per world unit for your first attempt. You can increase it afterwards when you are certain about the achieved light balance, as it will only refine the shadow and details, but at the cost of a much longer rendering time. Now you may press Bake Scene. Double-check the console for possible error messages. If all goes well, you'll see a blue completion indicator in the bottom right of your screen during rendering. After a few seconds or minutes, you'll hopefully have your baked light. Unity automatically sets the correct maps on top of the geometry and adjusts the shaders properly. Use the third or first-person character in our scene and walk around the model to see how it looks. Notice that while the sun is pre-calculated, our third-person character is still casting real-time shadows from the sun. If you have a Pro license, you can also add bounce lighting using global illumination rendering techniques. And you can also use environment lighting, which will brighten up all non-lighted areas considerably. Finally, you can also use area lights to simulate diffuse lighting objects or light entering a room through the windows. It even supports light-emitting materials if you use the right shader. Without a Pro license, you will have to mimic these effects. For instance, by adding additional fill lights on places where bounced light would appear. Luckily, ambient occlusion is still available, which ensures that you get more profound lighting and accentuated object geometry. Remember that the calculation of light takes some time initially, but there is no need to calculate lights in real time anymore. This is especially valuable for mobile devices if they have enough memory to store the light map textures. In this video lesson, we calculated our lighting using the integrated light mapping from Unity. This concludes section 4 on lighting. In the next section, we will introduce animation techniques. This is the first video of section 5 on animation. In this video, we introduce the animation system of Unity, which we elaborate throughout the next videos to open doors, set up a simple elevator, and create a sun study. Before we get to work, it is important to understand the basic concept of animation. In addition, since Unity 4.x, two animation systems are available: the legacy and the mechanism system. Finally, full use of animation requires scripting to ensure that animations are run at the correct time or event. Animation simply comes down to the fact that certain attributes or properties change over time. When a game object changes its position frame by frame, it is animated. Some animations are created on the fly, like moving around or turning a camera, while others are defined in advance, like the body motion of 3D characters. Pre-recorded animation is stored in clips, and they are assets, files, that are stored in the assets folder. The original third-person controller from the Character Controllers Unity package was set up with the legacy system, whereas the new one uses mechanism. Legacy animations are kept in an animation component, which references animation clips of the legacy type. For instance, idle, walk, jump pose, and run. This component also provides a default clip that can be launched when the game starts, if the play automatically option is ticked. To toggle the other clips, scripting is required. When you select a single animation clip, it is tricky to check whether it is a legacy or a mechanism clip. When you only see a few parameters in the inspector, you have a legacy animation clip. This is rather important as the animation component only accepts legacy clips. On the other hand, when you create new animations, by default they will be of the mechanism kind. Go to Game Object, Assets, Create Animation. In the inspector you see several additional properties available. And when you drag the new animation clip onto an object, Unity will not add an animation component, but rather an animator component, and also create a new asset with the name of the object, an animation controller. This controller can be configured in a more graphical way and can be used to define multiple animation clips that need to be triggered and blended together. This is where you set up the mechanism animation system. Beware that it goes much further, especially when you set up moving characters, but this is beyond our scope in this video series. And finally, to do something more elaborate, like to play different animation clips in different situations by reacting on key presses, this requires scripting. In this video lesson we did not really do much, but we defined the basic terms for animation and pointed out the two different animation systems available in Unity. In the next video, we will actually create an animation from scratch, when we make a cube rotate automatically. This is the second video of section 5 on animation. In this video, we explain how we can define an animation clip to make a cube rotate around in a looping mode. We will create a new animation clip and assign it to a game object. We will then refine the actual movement in the clip to better set how the movements will be performed. This is using the widely known keyframe method as used in Adobe Flash or other animation software. You define main animation keys at particular frames and the computer will do the interpolation between these keys. In Unity, we start simply with a single cube game object, positioned at the world origin and without any rotations set. This is rather important as these values will be steered by the animation clip, replacing whatever value is set manually. Please remember this. Create an animations folder in your project tab and open it. Now call Assets Create Animation in the menu, and when the new asset is displayed you can directly type a suitable name. Call it Rotation Loop to indicate what we want to use it for. Now drag the animation clip we just created onto the cube object in the scene view. Two things will happen. The cube object receives an animator component and a cube controller asset is created. The controller is automatically assigned to the animator component and ensures that the new clip will act on the cube game object. With the cube selected, open the Animation tab from the window menu. This opens a new floating panel, which you can dock wherever you want. The rotation clip is already visible, ready to start recording animations. Right now, nothing will happen when you press the small play button on the Animation tab. We need to add one or more animation curves first. Press Add Curve and browse to the rotation entry underneath the transform to press the plus icon. Once a curve is added, you can fold out the rotation line and look at the rotation Y parameter. It has two keys already defined, indicated by the small diamond shape on the timeline. The red line is a time indicator. Drag the time indicator to the last key position or use the forward-backward buttons to ensure you are adding the rotation Y value at the right time. Set a new value to 360 to ensure the cube is performing a full rotation over the indicated time frame of 2 seconds. Internally, Uni samples these animations clips at 60 frames per second. Press the small play button to check that the cube is effectively rotating. To fine-tune the animation interpolation, you can toggle the curves display mode, which gives a graphical view on how the parameters evolve over the time frame. In this example, we get a linear interpolation between 0 and 360 degrees, which works fine for a continuous looping rotation. We can now play the game and see our cube rotating once in the game window. To make it loop, adjust the animation clip properties in the inspector and activate loop time. Press play to confirm. In this video lesson, we created a new animation clip to make a cube rotation around its y-axis. In the next video, we will expand this to have a nice door opening animation with smooth transitions. This is the third video of section 5 on animation. In this video, we set up and keyframe a simple door that opens smoothly using an animation clip. Our door will be a simple cube, but we need to add an additional object to act as a hinge. This way, the animation clip will rotate the hinge and the door will follow automatically. Our setup is very simple. We create an empty game object called hinge in the origin. Create a cube game object and call it door. Drag the door onto the hinge so it becomes a child. All we need to do now is position and scale the door to ensure its corner is in the same place as the hinge. We need such a setup, as otherwise the door would rotate around its own center instead. To test if this setup is working, you can rotate the hinge around its y-axis. The door should follow the rotation, but around the hinge instead of around itself. Before we create a new animation clip, ensure the hinge is selected and not the door. Press Add Curve and add a new curve for the rotation parameter. To have a smoother animation, we will add a few different keys. We need at least 4 of them for the different positions. Right before opening, reaching completely open, right before closing, and fully closed. Use the Add Key button and move the keys to adjust the speed of the movement. Now we can set the values for the rotation Y parameter at 0, 90, 90, and 0 respectively. If you press play now, the door opens, stays open and closes again, but rotates a bit too far. The automatic interpolation can be seen when we switch to the curves display mode. To ensure the door stays cleanly at 90 degrees when open, select a key, the yellow dot in the view, and right-click on it to define its tangent direction. Set it to flat for all 4 keys. Now press the play button to test how the door animates more smoothly. It looks fine, but right now it immediately opens again after closing. We will return to this problem later on when we introduce scripting. In this video lesson, we got our hands on the actual animation curve of the door and adjusted it for a nice smooth transition between closed and open. In the next video, we will create a simplified elevator setup with 2 sliding doors and a rising platform. This is the 4th video of section 5 on animation. In this video, we expand our animation capabilities by setting up a construction with multiple moving objects. We start with 2 doors that need to slide open. The trick is to attach them to a single parent object, which will contain the animation for all its children. The platform is also added to this setup in the next step. First, the main setup. Create a box for one of the doors. Call it sliding door and scale it into a door. Duplicate it using Ctrl or Command D and position the 2 doors side by side. Keep the origin at the bottom corner between the 2 doors. Attach them both to an empty game object called elevator. An additional box is needed for the platform, which is also parented to the elevator. Now create a new animation clip called Elevator Animation. And drag it onto the elevator to link it and automatically add a controller for it, which will be named Elevator. Select the elevator game object and add curves for the transform position parameters of its 3 children. We add keys to define a movement in the x direction for the 2 doors. They start at x equals minus 0.5 and plus 0.5 respectively. And they slide 1 unit or 1 meter to minus 1.5 and plus 1.5. And then return to the start. Drag the keys far enough onto the timeline so the animation will be slower, taking more frames. For instance, 2 full seconds between each key. Just as with the door from the previous video, we need to set the tangents to flat for a correct movement. The platform will start to move after the doors have closed, so continue to add keys to the platform position at later time frames. Set position Y at 0 after the doors closed and at 2.0 a few seconds later. Don't forget to set the tangents to flat as well. Now you can play the full animation and adjust the position of the keys in the dope sheet view to tweak the timing properly. This is not a fully finished elevator, as there would be additional doors when we arrive at the next floor, but this explains the basic setup of a more complex animation involving multiple objects. In this video lesson we made a very basic elevator with 2 sliding doors and a rising platform, all attached to a single elevator object. The Animation tab gave us precise control over timing and interpolation type. In the next video, we will finish our animation introduction by creating a sun or shadow study. This is the fifth and last video of section 5 on animation. In this video, we create a sun study by animating a directional light with shadows. The animation of the sun's orientation, the altitude and the orientation, is made more intuitive by linking the directional light to a parent object, which will receive the orientations. We will also animate the light color to improve the mood differences between morning, noon and evening. We start from a basic scene with one of our architectural models. Create an empty game object in the origin and call it Sun. Add a directional shadow casting light and call that Sunlight. Position it at x0, y0 and z minus 10. Make the sunlight a child of the sun. The positioning of the sunlight is technically not necessary for lighting, but it makes the setup easier to understand for the scene editor. If you now rotate the sun using the x value for altitude or height and the y value for orientation or azimuth, you can see that the sunlight nicely follows the movements. Create a new animation called Sun Study and drag it onto the sun to create a controller and link them together in one step. Create the rotation curve for the sun, not the sunlight. Now set up the keys. Set x to 0 and y to minus 90 at the time frame 0. X to 45 and y 0 after 150 frames, that's about 2.5 seconds. And x to 0, y to plus 90 at 300 frames, or 5 seconds. When we play it, we see the sun describing a circular movement around the scene. To define our sun study, we can also animate our sunlight color. Add an additional curve for sunlight for the light color value. Set the color at time 0 to a dark orange. Apply a bright yellow at the second key. Finally, a dark purple at 5 seconds. This mimics the shift in hue and brightness throughout a typical day. Again, when you press play now, you get the animated sun with its moving shadows, but only once, as a default for an animation clip is to not loop. One thing we did not cover here is that imported models can also have their own animation clips. The third-person character model is a good example, but you could also prepare opening doors or more complex movements, such as an escalator, directly in your 3D animation software. In this video lesson, we created an animated sun, where not only the position of a light changes, but also its color. This completes our section on animation. The next section will introduce you gently into scripting. This is the first video of section 6 on scripting. In this video, we introduce the Unity scripting system and create our first script. We briefly introduce scripting and then dive straight in, heads first. We open the Unity manual, user guide, asset import and creation, scripting. You can access it online or offline. Unity supports scripting to define custom behavior and actions that need to occur in our interactive project. Games and interactive applications require several scripts. Through scripts, you can transform objects, react on clicking, run animations, or load new scenes. Scripts are assets, text files, with code that gets compiled into your game. You drag scripts onto objects to add behavior and set the script's variables to customize it for your scene. Unity supports different scripting languages: C#, JavaScript, and Boo. Most tutorials use JavaScript to target people with a background in web development. But we opt for C# as it resembles more to C++ and Java and adheres better to strong typing and object-oriented programming styles. But you can mix and match them both in your projects. Right now, when you added the character prefabs, you already used scripts. They added a custom behavior such as reacting on keyboard presses and moving the mouse. Select any script asset to see a preview of the code in the inspector. We aim to create a few reusable scripts in this video tutorial series. The ideal script is short, has a clear purpose, and can be used without further editing. Furthermore, scripts usually use public variables to allow you to change their behavior without requiring code changes. From the Assets menu, we can create a new C# script. You should immediately give it an appropriate name. Type rotate object. To assign the script, drag it on top of a game object in the scene. If you open the inspector, you see that a new script component is attached to the object, with the script's name rotate object. The name of the component is slightly rephrased for better readability. So far, Unity created a default script that effectively does nothing at all. If you press play now, you will not notice any difference. We will have to write the code to tell Unity what we want to occur. In this video lesson, we learned about the Unity scripting system and generated a default script that does absolutely nothing at this moment. In the next video, we will write a usable script to open a door when the player gets close enough. This is the second video of section 6 on scripting. In this video, we'll edit the script we created in the previous video, as that simply did nothing. Inside Unity, you get a preview of the script in the inspector, but you can't edit it there. Luckily, Unity includes a complete scripting editor called MonoDevelop when you installed Unity. While it is possible to use another editor, we will stick with the default one. To open MonoDevelop, double-click the freshly created script in Unity Assets tab, and MonoDevelop will be automatically launched. The software behaves the same on Windows and OS X. MonoDevelop is a so-called Integrated Development Environment, or IDE. You can edit the code, use automatic completion, syntax coloring, and even run and debug your code. On the left, you see a project solution structure, with all scripts and a whole set of additional folders that are used in the background to translate the script code into the compiled version that Unity runs. We mainly focus on the central editor view, where multiple scripts can be opened, each in a different tab. The tab displays the name of the script. Let's first inspect the default script. The first two lines load the libraries or assemblies from Unity and from Mono. Mono is an open source .NET framework which powers the Unity scripting system. You get the definition of your main class, which needs to have the same name as your script file. This class derives or inherits from Mono behavior. And then we have two empty default methods. They are preceded by a comment line after two backslashes that explains what these functions do. Start is called once when this object is first created, usually when you press play. Update is called continuously upon every frame refresh. Here you write code that needs to react on what happens in the scene. To illustrate this, we will write a simple log message to the console in both functions. Inside start, write debug.log, open the brackets, open the parentheses, we have started, dot, close the parentheses, close the brackets, and semicolon. And in the update, write debug log update is called. Save the script in MonoDevelop and switch back to Unity. If you have no syntax errors, Unity will automatically parse and compile the code and make it available in your project. Press play and watch what happens in the console tab. You should see a single "We have started" message and a whole stream of update messages. If you activate the collapse option, repeated messages are only displayed once, which is useful for this update message. If you write an error, Unity will complain in the console. Switch back to MonoDevelop and write a stupid error in the start method. For instance, change debug into debuggy and save the file. If you now come back into Unity, you get an error. Double-click on the error in the console and Unity steers you back to the place in your code where the error was first found. In this video lesson, we edited our first script in MonoDevelop and tested it in Unity. We also learned how Unity helps us getting back into the code when errors are discovered. In the next video, we will create an actual usable script that rotates a door. This is the third video of section 6 on scripting. In this video, we create a simple script that rotates a door when our player gets close enough. We will show a simple rotating door setup with a hinge and a trigger. Then we write code that reacts at the right moment to turn our door. Finally, we attach a script to the correct objects. It is essential with scripting that things happen at the right time or event. Our script will use the integrated collision or trigger system of Unity. Collisions occur when objects that have a collider bump against other colliding objects. Remember that we needed colliders initially to not fall through the floor of our model. This is the same system. Triggers also use the colliders, but they don't obstruct other objects. They simply register when a collider enters and leaves its volume. Our setup is very similar to the setup from the animation video. An empty hinge game object with a cube for the door attached at the right position. When you turn the hinge, the door follows. Open our rotate object script in MonoDevelop by double-clicking it in the Assets tab. Remove the debug statements from the previous video and write a new statement in the Start section. Type this dot transform dot rotate with a capital R, open the brackets. At the moment you type the bracket, a pop-up appears that shows hints at a possible variance of this method. We'll add 0, 90, 0, close the brackets, and end with a semicolon. Save the scripts when you are sure that there are no syntax errors and switch back to Unity. Attach this updated version of the rotate object script to the hinge game object in the scene. Press play and see if the door opens when the script starts. Check the inspector. That's fine, but we can do better. The door opening should happen only when our player gets close enough. So, add the third-person character we saw earlier. Now also add a new cube. Mark it as trigger in its box collider component and disable the renderer so it becomes invisible. Go back to our script and add a new method that gets called automatically when a trigger event occurs. Void space on trigger enter, open the brackets, and as a parameter, class of the type collider, and its name other. Close the brackets and then open the curly bracket. This replaces the previous call to the rotate command, which was placed in the start method. Add an additional method called onTriggerExit with the same parameter. And add the same code but now with a negative angle minus 90 degrees around the y-axis. Save and test. Notice that it doesn't work correctly. The trigger event needs to be captured by the trigger box, whereas the rotations should occur on the hinge object. So remove the script from the hinge and add it to the trigger. Now open the script again and add a public variable to set on which object the rotation should occur. By adding a public variable, it becomes editable by the user in the inspector. It also allows you to reuse the same script on other objects with the different values for this variable. Make the variable public of the class game object and as a name target. Replace this in the code with target in our script. This variable can contain any game object. It can be a cube, camera, a light, or a model. So any object in the scene is acceptable as a parameter for target. Now save the script, switch back to Unity. We have to drag the hinge object onto the target variable field, so the script will act on the right object. Press play to test our setup again. Now, whenever our player enters the trigger box, the hinge rotates 90 degrees and the door, which is attached, will open. Hooray! Our first actual script is running. Congratulate yourself and then understand that this is only the beginning. There are multiple improvements that could be made, smoothing out rotation, reacting only on the player and not on other objects, but this suffices for this lesson. In this video lesson, we set up a door that automatically opens when the player gets close enough, using a trigger event. In the next video, we'll look at how we can switch materials and learn about using a list of objects. This is the fourth video of section 6 on scripting. In this video, we set up a more advanced script that allows you to switch a material while running the game. This requires us to learn 3 new techniques: working with the list of objects, changing a material at runtime, and reacting on keyboard presses. So switch back to Unity. Our basic setup is simply one cube, one light to see something, and a few materials prepared in the assets folder. Add the new C# script and call it switch materials. Double-click it to open MonoDevelop, and we are ready to start. First thing we need is a list for all possible materials, by defining a public variable as an array of materials. Arrays can contain several objects or values and are easy and fast to step through. Write public, then the class material with 2 square brackets, and as a name materials, which creates an empty array. Save the script and switch over to Unity. Drag the script onto the cube object. When the script is compiled, a new variable called materials is displayed as an empty list in the inspector. You can now drag materials onto this variable and they will be added to the list, which expands automatically. But since our script does nothing at the moment, we have to return to MonoDevelop. We want to do something whenever we press the M on the keyboard. Within the update method, write if, open brackets, input dot get key up, open the brackets, key code dot m. Notice that MonoDevelop displays all possible options when you type the dot. This is called auto-completion and helps you when coding. Close the brackets twice and then open the curly brackets. This method will be true at the moment we press and release the M button, indicated as the keycode.m value. The renderer component is where the list of materials for an object is stored. We can access that component in our code. Write this dot renderer dot material and set it equal to materials with square brackets 0. This sets the main material of the object to be the first material from our list, which is indicated by an index 0. Like most programming languages, arrays in Unity start counting at index 0 instead of 1, so be careful. Save the script and press play. Whenever we press M, the cube switches to use the first material in the list. Almost there. We'd like to switch to the next available material with each additional key press, so go back to your script in MonoDevelop. we'll maintain a variable to remember which material from the list we have set. We'll use an int, which is short for an integer, which allows only discrete positive or negative numbers without a fractional part. Write private int index at the beginning of our class definition and initiate it to 0 in the start method. Index equals 0. Since this variable is set to private, it will not show up in the inspector and is only used internally in the script. In the update method, we use the index variable. This .renderer.material equals materials, but instead of 0, we now use index. And finally, increase the index by 1. To ensure that we don't get past the end of the list, which would generate an error, also use the modulo operator. The modulo gives a remainder after we divide by the given number. And use the modulo operator with the length of the array. So we fall back to the first index after the last one. Index equals index plus 1 between brackets, then the modulo operator, the percentage sign, with the length of the array, which is indicated by materials variable dot length. Now save the script, go back to Unity and press play. Click the M button a few times to see that we shift through all materials in the list and that we skip to the first one after we arrived at the last material. Congratulations! Your second fully functional script. In this video lesson, we set up a script to toggle materials for an object. We learned about using an array to keep a list of objects. We reacted on a key press, and we used some math to loop through our list using a private index variable and the modulo operator. In the next video, we will refine this script with a small user interface, an on-screen button. This is the 5th video of section 6 on scripting. In this video, we expand our material switcher from last video and add a small, simple user interface to it. Graphical user interfaces, or GUIs, are very important in real-time applications. They are easier for an end user, and they work also on mobile platforms with touchscreens, where keyboard shortcuts are non-existent. Unity has a GUI class and a dedicated onGUI method where we can set up our user interface. As we will make this improvement in our previous script, switch back to monodevelop and the switch material script. First, add the GUI event, void onGUI. Open and close the brackets and open the curly bracket. Be sure to use the correct capitalization, or the method will not be recognized by Unity. Within the onGUI method, we can use the methods in the GUI class to add user interface elements. In this example, we use the button method. Write GUI.button and open the brackets. As a first argument, we need a rectangle to define the position and size of the button. Let's create an instance of the rect class. New rect and open the brackets. We now have to add 4 float numbers. Horizontal position, vertical position, horizontal size, and vertical size. Let's use 10, 10, 120, and 20. Close the bracket. Positions are defined in pixels from the upper left corner of the screen. As a second argument, we write a string between quotes to define the text that is displayed on the button. Label it switch material. Close the brackets and end with a semicolon. Test the script by saving and running the scene in Unity. If you didn't write any mistakes, you should see a button displayed above the game view. GUI elements are only visible when running a game. Now press the button. Nothing happens, as there is no reaction written for the button pressed yet. Stop the game and go back to monodevelop. If you press a button, the method will return a true Boolean value. So we can now add an if control method around the GUI button statement and react on the button being pressed. Simply copy the 2 lines of code that we put underneath the update method and paste them in the if statement. Now save and test your script. You can still use the M shortcut, but now you can also press the button labeled Switch Material. In this video lesson we added an on-screen button to our script using the GUI class in the onGUI method. Buttons and other interface elements are good, as they don't require a manual and work equally on all platforms. In the next section we will take our scripting efforts a step further. Take it or leave it, but in most interactive projects a certain level of scripting is required to get any results. But rest assured that we'll take easy, small steps that are still very relevant to apply in other projects. This is the first video of section 7 on scripting. This section will expand our scripting knowledge from section 6. In this video we'll add a list of toggle boxes on screen to hide or show pre-selected game objects. Hiding and showing objects can be used to allow the user to control the visibility of design options, to hide building parts, or to toggle the display of furniture. We will first collect a list of objects that we want to toggle. Then a toggle box will be displayed as part of our user interface. And finally, we need to traverse the list of objects to effectively hide or show them on screen. We start from the building model we already used in the previous sections. Check the hierarchy, play with the active checkbox and the mesh renderer component, which can be deactivated too. Both can hide objects, but will focus on the active state in our script. Create a new C# script and call it toggle objects. Open it in MonoDevelop. To be able to handle a list of game objects, we use an array variable. Write public class game objects with square brackets to indicate that it's an array, and as a name objects, and with a semicolon. Then we want to add a series of toggles for each object in our list, which we will use to show and hide them. This is done in the onGUI method. With the for each, we step through all game objects in the objects array. In each step, we can use the go variable to access the array item. So for each game object, go in objects. Close the brackets, open the curly brackets. We use GUI layout, which provides automatic placement of GUI items, so we don't need to add a separate rectangle statement here. The value of the toggle, which can be on or off, or true or false, will be the active self property of the object. And the text that is displayed is simply the name property of the object. Save the script and test it in Unity. We create an empty game object and drag the script to it. Now we can configure the array by dragging some objects from the model onto the list. Press play to test the script. You should see 3 toggles in the upper left corner of the game objects. But the toggles are not functional yet. Stop and switch back to MonoDevelop. We now add a bool variable with name active that captures the result of the toggle function. If this variable differs from the active self property of the game object, then we will toggle it with the returned value. So if active is different from go.activeSelf, then we call go the method setActive, and as a parameter the active boolean. This ensures that objects are only toggled when we effectively click on one of the toggles in the game view. Save and test again. Now you can hide or show the objects you configured in the array. Beware that this method activates or deactivates an object and all its children at once. This is easy to do, but also deactivates any scripts and other components that are running on these objects, so be careful what you toggle. In this video lesson, we learned how to change the active property of game objects in a script. We used the GUI layout toggle method to display the different toggles on screen and let Unity take care of hiding objects and their children. In the next video, we will make a script to switch between different viewpoints. This is the second video of section 7 on scripting. This video will let the user switch between different viewpoints by using different camera objects. You can use multiple cameras in a scene. However, if they are all displayed on the whole screen, they overlap. The approach we use is having a different camera in front with a high depth value and let it move smoothly between the other camera positions. We continue with our regular scene and add a few different cameras. We call them Cam 1, Cam 2, and Cam 3 respectively. Also, add an additional camera called Master Camera. For a better overview, we make all the cameras children of an empty game object called Camera Group. A nice way to position cameras is by finding a suitable view position in the scene window, using orbit and pen movements, and then select the camera and align it to the view using the menu Game Object, Align with View. Create a new C# script called Switch Camera and open it in MonoDevelop. First, add an array to store our cameras. Public, camera with square brackets, and as a name, cameras. Also, add a single camera as master. Public, class camera, and as a name, master camera. Semicolon. In the start method, we step through the list of cameras and set each one's depth to -10. The master cam gets depth 1 to ensure that it is displayed above the others. Then we'll use a private integer variable called index to keep the chosen camera number. Set it to 0 in the start method and switch to the next index in the onGUI method when pressing a button. Use GUI layout, so you don't have to worry about button placement on screen. We'll use the same modulo operation as we used with the material switcher video. So if GUI layout button called next camera, that returns true. We change the index, index +1, modulo camera's length. Almost there. We still have to ensure that our master camera is moved to the right place. Do this in the update method. Set the position and rotation parameters by copying them from the camera in the array at the position index. Save the script and switch back to Unity. Now drag the main camera, Cam 1, Cam 2 and Cam 3 to the camera list and set Master Cam as the master camera. Now press play. Hit the next camera button a few times. A possible improvement is to use LERP, short for linear interpolation, to move the master cam smoothly to the right position and rotation. LERP is a static method called from the vector3 and quaternion classes, with arguments from and to position or from and to rotation. And a small number to set how fast the transition will be calculated. By setting this in the update method, it gets refined continuously. Now save the script for a final test run. In this video lesson, we created a small script that allows us to switch between cameras at runtime. Use this to prepare some particular views on your product or design. You can switch between players or even to an animated tour of your project using an animated camera. In the next video, we take control over the player. This is the third video of section 7 on scripting. In this video, we will control what happens when the player will bump into a trigger. This can be used to reset his position when he falls from the world or return him to a particular location in the scene. We do this using a trigger box. The position and rotation of the player can be stored automatically, but we also illustrate an alternative using a custom spawn point, as it is often called in game terminology. We use a simple scene with a building and a third-person character as the player. Just ensure that the player correctly received the player tag. Create a new C# script, call it reset player, and open it in MonoDevelop. Create 3 private variables: private GameObject player, private vector3 pos for position, private quaternion rod for rotation. Vector3 objects keep XYZ positions, while quaternions are an equivalent class for rotations, but they are mathematically a bit more complicated for numerical robustness. However, we don't have to bother about their implementation. In the start method, we query our scene for the player object using the findGameObjectWithTag method, which can be called from the GameObject class. As an argument, use the player string, which was the tag we set up initially. With this object, it is trivial to store the initial position and rotation in our 2 private variables. This is nice as there is nothing we have to set up. There are no public variables at this point. This script will work from a trigger object, so switch to Unity, create a simple cube, and set its collider to isTrigger in the inspector. Back in MonoDevelop, We need to also implement the onTrigger method, which is called whenever an object passes through the trigger. First, check that it is the player who hits the trigger by comparing the tag of the collider with the player string. If other game object, compare tag, player. If that is true, then, if that is the case, we can simply recall the pos and rot variables to move and rotate the player back into his original position. Save the script, switch back to Unity, and drag the reset player script to the trigger cube. No need to set up variables, just press play. Walk towards the cube and notice how the player is placed back onto the original starting position. And because of the third-person camera script, you get a smooth camera movement for free. But we can improve our script further. Switch back to monodevelop. If you want to move the player to a custom spot, add a new public game object variable called custom spawn point to the script. In the onTrigger method, you can check for the availability of this variable. If it is not null, which means if it exists, then use the position and rotation from it. To test this, now you do need to add an object to the public variable field. You can use an empty game object, as not to obstruct the player when resetting. Here we place the spawn point on top of the roof of our building. To visualize the custom position, you can use a color indicator from the inspector. This makes the empty object visible in the viewport of the editor. A final save and test should confirm that the reset trigger works as expected. In this video lesson, we set up a system to reset and reposition our player by using triggers. We also learned about retrieving particular objects from the scene using a tag. In the next video, we look at picking objects on screen when running the project. This is the fourth video of section 7 on scripting. In this video, we'll learn how we can pick an object on screen. This is useful to select an object for more information, such as displaying material, cost, or structure data. Picking objects can be done casting a ray, which will traverse the geometry and return the closest object it collides. The resulting hit point can be queried for certain feedback, such as which object was hit and at which point. And finally, to give some visual feedback, we display the name of the object to the user in the GUI. This approach works with any scene, so we continue from our last model. There's nothing in particular to set up, apart from the fact that you can only pick objects which have a collider geometry, like a box, sphere, or the geometry you imported using mesh colliders. We already generated colliders from the FBX importer settings, so we are good to go. Create a new C# script and call it pick object. open it in MonoDevelop. In the update method, we will start by checking if we hold the first mouse button down, which is usually the left mouse. This is called from the input class, and we check for button number 0. Input dot get mouse button, open the brackets, 0, close the brackets. Next, we set up array and arraycast hit, which is a structure that is returned by the arraycast method. When we cast array, we do this as a line between our viewpoint, which is the camera position, and the current position of the mouse, which also conforms to a position in the 3D view plane of the camera. We use the convenience function screenPointToArray and call it from the main camera as provided by the camera class. As an argument, we use input mouse position. The execution of the raycast is done by the physics class, and the empty hit variable we created will be filled in, if the function at least answers with a Boolean true value. The number 20 is how far we want our ray to be cast. If we pass the if control, it will contain several parameters. The normal of the geometry at the hit point, the distance from the starting point of the ray, and the objects with which we collided. To check what we are doing, we write a debug log message containing the name of the collider we hit. Now we can save the script if all brackets are correctly closed. And in Unity, attach it to an empty game object called GUI. Press play and click into the scene, while keeping an eye on the console or status bar. You should see the debug message appearing each time you click onto an object. However, we want to present this information to the user, as the console is only usable during project development. So keep a private variable to maintain which object has been picked. Private, game object, hit object, semicolon. When we pick the object in the update method, set a variable to the object we just picked. Hit object equals colli.gameObject. If we did not pick any object, we have to set the hit object back to null. Do this in the else part of our if control statement. In the onGUI method, we display a box with the name of the object, but only if the hit object is not null. Get the name of the hit object and use it as an argument for the label function of GUI layout. No need to set up size and position with GUI layout methods. When we save the script and return to Unity, we can now check if it works fine. Press play and click on some of the building elements. Their name appears in the upper left corner and stays there until we click on the background or hit another object. This is not perfect and graphically it could be refined, but the basic mechanism is now implemented. By the way, since we check for the first mouse button, this approach also works on mobile devices, as a touch on the screen is also registered as a left click of the mouse. In this video lesson, we implemented object picking using the raycast method of the physics engine. We retrieved information from the picked object and displayed it using a label. In the next video, we will refine the script by requesting additional information that we can store per object using a custom data component. This is the fifth and last video of section 7 on scripting. In this video, we expand our script from the previous video and not only display the name of an object, but also check for additional custom data that we attach to it. We will create a simple script to add a few additional variables to an object in a custom component. When we pick an object, we can retrieve this information through the component and we'll display it in a pop-up window properly centered in the screen. Just continue with the scene from last video. In Unity, we create a new C# script and call it object data to store some information about the building element. Open the script in MonoDevelop and simply define a few public variables. Public, string, short name. Public string description. And public float total cost. If you add the multi-line between square brackets statement directly before the description variable, the text will display it as a multi-line editing text. Save this script and attach it to one of the main wall objects in our model. Since object picking is only possible with colliders, we need to ensure that our data is attached to the mesh object that has the mesh collider and not on one of the empty parent objects. Write in a few strings to define the data. Now we need to adapt our pick object scripts we created in the previous video. We go straight to the onGUI method and expand our code a bit to retrieve our custom data if available. First, on the hit object, use the getComponent method to retrieve our custom component. The syntax itself is a bit particular. GetComponent, use angular brackets with the proper class name object data and curved brackets without arguments. We also have to check if this component actually exists, in case we did not add the object data script to a particular object. It is easiest to assign this to a variable of this class so we can directly request the properties. And to be able to access the variables of this class, we need to cast it into the object data class. Finally, we simply add a few GUI layout label statements to place different parameters on screen easily. GUI layout, label, then hit object name. Do the same for data short name. Data description, data total cost, and translate total cost with this toString method into a value that can be displayed in a label. If no object data is retrieved, we simply use the name of the hit object. Save the script and play the scene. Click on one of the objects to which object data was attached. You should see the additional parameters when available, and only the object name if no custom object data component was retrieved. Here we first calculate 1/3 of the actual screen using screen.width and divide it by 3. Assign this to a local variable screen_third. To center our text labels, we can group the labels in an area. Place GUI layout begin area before the labels, and as argument, we define the required size using a rectangle. New rect, screen_third. This is then used to set the rect position and width. You have to end with a call to GUI layout end area without argument. You can even make some of the text editable by replacing the GUI layout label with a GUI layout text area. However, you need to ensure that the return value of this method will be assigned to the actual data description value, so it can be overwritten. We also added a min height option, so the field has some height. This keeps the edit text as long as the project is running. To actually store it permanently with the model is beyond the scope of this particular video, alas. Test the final version of our script and try to edit the description field for the selected object. In this video lesson, we enhanced the pickObject script to add custom object data and displayed it on screen. We also made a description value editable, which could be used as a primitive commenting system. This concludes section 7 on scripting. The next section will turn our Unity project into an actual application that you can share. This is the first video of the final section 8 of this course, where we prepare our final walkthrough as an app. In this video, we discuss the project build settings. So far, our project ran in the Unity editor, but this is not a format to share it with others. The project needs to be built into one of the supported application formats from Unity. We need to configure the build settings of the project. This requires that you add the necessary scenes to the build. We also set up some project information in the player settings. In Unity, we access the build settings dialog from the file build settings dialog. Here you get a list of all supported platforms, which depends on your Unity license. Users of the free version of Unity can target a web player for browser games, standalone applications for PC, Mac and even Linux, and mobile users such as iOS or Android. Users of Unity Pro need to use the Pro versions of the mobile add-ons as well. Some platforms are only supported if you run on a compatible operating system, such as OS X for iOS apps and Windows for Windows Store or Windows Phone. Press Add Current to add the currently loaded scene into the scene in the build list. You can also drag scenes from the Assets tab into the list and even change the order in which they are loaded. The first scene in the list is what you'll see when you start the game. Switching to other scenes at runtime requires scripting. From this dialog, you can also open the player settings in the regular Inspector tab, which control the export process. Set your own company name and product name now, and it would also be good to set a default icon here. You can use any image you loaded in the project, but it is best to prepare a square image of sufficient resolution, for instance 256 by 256 pixels, so Unity can properly rescale it when exporting and set its importer settings to GUI instead of the default texture. The bottom part of this inspector pane is used for a series of settings per export platform, although some settings are shared between the tabs, as indicated by an asterisk. If you press Build Now, you need to set up an output folder and a file name for the exported project. By default, Unity will export a standalone application for the platform you are currently using, usually Windows or OS X. Since we are using OS X in this example, we get a Mac OS X app, but the result on Windows is very similar. Double-click the application and you are greeted with the default Unity application configuration screen, with graphics options for screen resolution and quality, and a second tab page to set up controls, such as keyboard shortcuts or gamepad button and joystick assignments. Press play to launch the game. Try running around for a few seconds. Use Alt plus F4 on Windows or Command plus Q on OS X to quit the game. What just happened? Unity is not magically creating new applications, but is rather packaging a pre-compiled application with the required compiled assets and resources. This way, you can seemingly create a Windows executable on OS X and an OS X application bundle on Windows. In this video lesson, we set up our project to be built. By default, this is a standalone application for the platform on which we are currently running the Unity editor. In the next video, we take a look at the web player output. This is the second video of section 8 on setting up our final exported project. In this video, we switch to the web player output format. Out of the box, each version of Unity supports the export of a project into multiple platforms. By switching to a different build platform, Unity automatically reorganizes and optimizes all imported assets to a more suitable format. We will target the web player format, which is a cross-platform approach to share Unity projects online. The end user needs to install the Unity web player add-on, which occurs automatically, but which only targets recent operating systems and browsers on desktops only. In the near future, Unity will also support WebGL, so the browser user doesn't even need a plugin. The export will create a single Unity 3D data file and an HTML page derived from a template, with the necessary loading code to install and launch this player. This can be tested directly on your computer, but you'll need to upload it to an online web server for others to be able to play your project. Go to the Build settings, select Web Player in the list of supported platforms, and then press the Switch Platform button at the bottom of this dialog. Right now you are ready to build, but it is good to go through some settings first. Press Player Settings to load the player settings in the inspector. Here you can define the width and height of your app, which is fixed for the web player, unlike a standalone application. There are 3 default templates included: a black and white background and one without right-click menu to remove some control from the user. The default is just fine. In the Build Settings dialog, you can press Build Now and set an output folder and project name. This time, Unity applies a special compression step to minimize the size of the export, which is still very important for online projects. The end result is a folder with 2 files. The HTML file is a template from the player settings, but filled in with the necessary code to launch our exported project. The Unity 3D file is the actual web player data. If you double-click the HTML file, your default browser will open. A script checks first if you have the Unity browser add-on available. If not, it is loaded automatically from the Unity website, provided you have sufficient permissions to install add-ons for your browser. Since the player is used online on different game and social media sites and is also installed with Unity, you will normally not have a problem loading the game, unless you are not online, since the JavaScript used to load a plugin is not included in the HTML file, as it is referenced from the online Unity website. You can set the offline deployment in the build settings if you want to include all required JavaScript files, so you can test the web player project offline. Even then, things can go wrong, so you are best to test the project with an active internet connection. If you want to present this project to somebody online, you need to upload these 2 files to an online web server, usually using FTP software. It might be handy to rename the HTML file to index.html, so the URL only needs to refer to the folder, as most web servers are configured to load index.html files in a folder as default page. In this video lesson, we switched to the web player platform and exported our project into a web page that can be played if we have the Unity web player browser add-on installed. It required no changes to our Unity project or scripts. In the next video, we switch to one of the supported mobile platforms, iOS. This is the third video of section 8 on finishing our project. In this video, we will transfer our project onto a smartphone. We use iOS and an iPhone as an example, but the process for other mobile platforms is very similar. The cross-platform support in Unity is excellent, but you need to ensure you use a compatible combination. For Windows Store or Windows Phone applications, you need to use Unity on Windows. And for iOS devices, you need to run the OS X version of Unity and have the required developer license to run the app on an actual device or to submit it to the App Store. We will switch to the iOS platform, check our player settings again, and build an app, or rather, a project that will build the app for us. Go back to the build settings. We can select iOS if you are using OS X and switch to the platform. This will take considerable time, as all imported assets are re-imported, but this time with another optimization settings that are more suitable for mobile platforms, such as using a different texture format and compression, and audio or video formats. Wait till the assets progress is finished. We will skip this in this video. When the process finishes, nothing is exported yet. This first step was only required for the setup and optimization of all assets. However, you see in the title bar of Unity that you are now targeting iPhone, iPod Touch, and iPad devices, all running the iOS operating system. And in the game window, you get a series of preset aspect ratios and resolutions that reflect the current set of available devices. Go back to the build settings again, but resist the urge to press build now. You need to configure the player settings first. There are a few things that you cannot afford to miss here. Set the product name and preferably the company name. The icon is also very important if you don't want a bland default. Check the resolution and presentation setting. The default is set to portrait, which might be not what you want in most cases. You can allow auto-rotation and set the allowed orientations too. We stick with landscape right and left and an animated auto-rotation effect. If you have an iOS Pro license, you can also choose a different splash screen. Now you can press Build in the Build Settings dialog. Choose a suitable output folder and let Unity do the compilation work, which can take a while. When this is finished, Unity displays the Finder with a folder of the exported project. This folder contains a full Xcode project, which requires the Xcode development system from Apple. This you can freely download from the OS X App Store. Double-click the Unity iPhone Xcode project file to open Xcode. Almost there, but not quite yet. In this video lesson, we converted our project without making any changes to the iOS platform and exported it as an Xcode project. In the next video, we will compile the Xcode project so the app can be transferred on an actual device. This is the fourth video of section 8 on finishing our project. In this video, we continue the previous video where we ended up with an exported Xcode project folder. This video, we will transfer the app onto an actual device. Within the Xcode project, we will look at a few important settings and then finally build and run the project. Last video, we double-clicked the Unity iPhone Xcode project file to open Xcode. The project is displayed fully configured to be compiled into an iOS app. You see on the main screen when selecting the Unity iPhone project in the left pane, many of the settings you prepared inside Unity, such as the supported display orientations and the name of the project, using the product name placeholder. If you make changes in the Unity project, you need to export the Xcode project again. But in this case, you can allow Unity to append all changes to the already created Xcode project to maintain certain customizations, such as initial code and classes you did not create in Unity. To get our app running on the device requires that you have configured everything you need for iOS development first. You need to be a registered Apple developer and have an iOS development program subscription or belong to an iOS development team. This is not free, alas. The setup requires you to register your specific iOS device to get a provisioning profile for testing. This will allow you to run a compiled application on the device. The setup is documented by Apple and is far too elaborate to explain in this short video. You can check this in the organizer in Xcode. With regular projects, there is nothing specific to set up in Xcode anymore. You can now build the application, Command B. This might take some time and could generate warnings or even errors. If you have everything set up, you'll get a succeeded message in Xcode. We see a few warnings, which are not problematic for our project at this moment. Now you can press the triangular Run button in Xcode now, which builds the runnable version of the app, transfers it to a connected iOS device and runs it with console output redirected to Xcode. This might also take some time. Press Stop in Xcode to properly shut down the app. From now on, you can relaunch it on your device as many times as required. While this video is specific to iOS and requires OS X, the processes for BlackBerry, Android or Windows Phone are comparable. Export the project and compile it before you can actually run it on a device. In this video lesson, we compiled and ran our Unity project on an iOS device. The biggest advantage we have is that the majority of our project can be developed for all platforms at once. In the next video, we'll wrap up this section with some final improvements. This is an additional video specifically to add a mobile controller based on the sample assets. If you go to the sample assets, cross-platform input and the prefabs, you can use the mobile single-stick control rig. This is set up to be controlled within Unity from the Unity remote app, which can be run from the iPhone. You can use your left thumb to steer the character and you use the right jump button to have him jump. This way you can test how it would behave before you actually compile it. Because everything is already set up, we can now directly call build and run from within the file menu. Project is translated again, the scenes are compiled, and everything is bundled together in one Xcode project. If everything is set up correctly and your iPhone or your iPad is connected, you can now go back to the project and recompile it. Call run directly to build the project, which can take a considerable time, and then actually activate it on the iPhone. So this is the output from screen capture from the iPhone. Final project, title, menu screen, and then you have the button to start the actual project in the bottom right corner. Exactly as it behaved inside Unity Editor, you can steer with the left thumb and jump with the right thumb. Okay, everything is ready. Now you can start roaming around, changing scenes, changing scripts, and combining everything we learned in the previous videos into one final project. Thank you for watching. This is the final video of section 8 on finishing our project. In this video, we make a few improvements to our project to wrap things up. To better assist our user, we will add a small menu or intro scene, add a simple logo, and add some help text. We also add a start and home button, which requires one small additional script. The menu scene can be very simple. We create a new scene and save it as menu. This scene is empty by default, and we'll liven it up a bit by adding an instance of one of our architectural models. Adjust your view to an overview perspective. And adjust the main camera to inherit this viewpoint by selecting the camera and choosing the game object Align with View menu. Now add a GUI texture game object. Call it logo and replace the default Unity logo with a more suitable image. We created a very simple Photoshop file with a transparent background and some nicely formatted and colored text. Our example is 512 by 128 pixels, which is a power of 2 size in each direction for optimal results. This is saved into the Assets folder, and when switching back to Unity, becomes available. Change the import settings to GUI instead of texture, and use 16-bit to not compress the quality away. Now the logo is placed above the screen. Find a suitable size and position. We set the transform position to x 0.5 and y 1, scale to 0, 0, 0, so the pixel sizes come into effect. And then use the pixel inset to move our image halfway, -256 and -128, and using its real size, 512 and 128. You can include a descriptive text as part of the logo, or use a GUI text game object, which acts similar to the GUI texture for scaling and sizing. We use position 0.05 and 0 to anchor it to the lower left button, scale 000 to enforce pixel sizes, set up the text anchor to the lower left, then type a simple text and press Alt-Enter when you insert multiple lines, a Y pixel offset of 20 pixels, finally a font size of 24. Be sure to rescale your game window a bit to check how this works out, as it can be quite confusing initially. We add a new C# script called switch level, as this requires some code. Open it in MonoDevelop and create 2 public string variables called level name and button text. Add a non-GUI method. Set up a simple GUI button in a rect that is 128 pixels wide and 32 pixels high. But align it to the lower right screen corner using the screen.height and screen.width properties. We added 10 pixels offset as well. Use application.loadLevel with the provided level name string. This is the only actual scripting part we need. Save the script, switch back to Unity and attach a script to any object you want. Set the two variables, scene name and name to be displayed on the button. Before it actually works, you have to ensure that the menu scene has been added to the build settings. Place it at the front of the list, so this is what the user will see first when starting your project. Press play to see the button being displayed. You can reuse the script in another scene to load other scenes or to return to the starting scene, the menu. You can also add additional, smaller logos in separate scenes if you want, maybe even turning them into a prefab. In this video lesson, we wrapped up our project with a small menu and a simple interface to switch between scenes. This was the last video of our series. While there are so many things you can still do, this is more than enough for our introduction purposes. Congratulate yourself, as you have achieved quite a bit throughout these tutorials. Thank you for watching and good luck with your own projects. My name is Stefan Boykens and I thank you for your attention.